You may not have heard of him, but Sir Francis Galton was a Victorian genius. The renowned polymath was born here in Birmingham, England in 1822 and was responsible for many notable scientific advancements in the 19th century, including the development of fingerprint classification, psychometric testing and the first weather map. He's even credited with inventing the questionnaire. But despite such accomplishments, perhaps Galton's most important and influential legacy is unknown to most people, hidden inside an obscure contraption named after him, the Galton board. Invented in 1876, the board was used by Galton to develop some of the most powerful concepts in yet another field he worked in, statistical mathematics.
He was very interested in biology and medicine and the application of mathematics to it. And particularly interested in how certain characteristics are inherited. That interest in passing on genes, as it were, was actually how he came up to be interested in statistics.
He was particularly curious about why certain human characteristics, such as height, instead of randomly varying within a population, appeared to vary in a very orderly, recognisable way, and specifically according to something called a normal distribution.
The normal distribution is often known as the bell curve. It's this curve which has a shape like a bell, so it's very high in the middle and low towards the edges, and it can be used to describe a wide range of naturally occurring phenomena, from heights, for example, through to IQ scores. Typically, a large number of people will be clustered around the mean behaviour, the average behaviour for a particular trait, be that the average height or the average IQ, but there will be some people who are way out in the tails of this distribution, but not very many of them. And so this bell curve characterises the frequency of occurrence of this particular trait in a population.
This phenomenon of normal distribution fascinated Galton, and what he wanted to do was to provide a practical demonstration of why it occurs. The Galton board does just that. The design consists of a vertical array of pegs ordered according to a quickhunks pattern. A large number of beads, introduced from a centre point at the top of the board, make their way through the pattern, eventually coming to rest in one of several bins uniformly arranged across the bottom.
What you find is that you get this really beautiful normal distribution mapped out by the shape of the beads. Now, the reason for that is that there are far more ways to get to these central bins than there are to get to the bins at the extremes. Now, each of these beads, every time it gets to a peg, it goes left or right with equal probability, 50-50. So if I'm thinking about getting out to this bin, then every time a bead hits a peg, to get out there, it has to go the same way every single time. The same if I'm trying to get to this other extreme. But in the middle, there are lots of different paths, sometimes going left, sometimes going right. And these left and right movements will somehow cancel each other out, and they'll end up tending to head towards the centre of this distribution far more. So this is the beauty of this Galton board. It generates this predictable normal distribution from what is effectively a random process.
Now, to be precise, the beads form what is known as a binomial distribution and not a normal one. But there's a good reason why we can call it a normal distribution.
A binomial distribution occurs when you have to make multiple binary choices, which is exactly what's happening in the Galton board. Now we have a tool in mathematics which is called the central limit theorem, which effectively says that if I have enough of these independent random variables stacked together, these binary trials when the bead hits a peg, which allows us to say that this binomial distribution is well approximated by a normal distribution.
The central limit theorem is arguably one of the most important in all of statistics. Essentially, it explains why the normal distribution is so commonly seen, particularly in social studies, such as Galton's into human traits.
We see the normal distribution a lot in the natural world because we have lots of these composite random variables adding together either give us an addition to that trait or a subtraction from that trait. It might be that there are a number of different genes which contribute to the final height of an individual, which will be inherited from parents. And there might also be a wide range of different environmental factors which contribute. Each one of these will be a random process, not necessarily determined beforehand. If you have very tall parents and you have good nutrition and various other beneficial factors, then you might find yourself being very tall, but actually it's likely that a lot of these composite factors will cancel each other out and you'll end up much nearer to the mean height, which is where this normal distribution comes in. And that's a consequence of this mathematical central limit theorem.
The central limit theorem allows us to use the normal distribution in a multitude of scenarios. From quantum physics to biometrics, from stock market returns to resource allocation and quality control. Customers arriving at a counter, telephone calls coming into a system, even the number of yeast cells used when brewing a Guinness can all be represented by the normal distribution.
These normal distributions occur in everyday life, and we can make a link between these abstract mathematical concepts and these real-world concepts. And I think the real power of this Galton board is to illustrate that we can find patterns even in seemingly random places. It's a whole series of random events, these balls moving through this array of pegs. It reproduces a reliable normal distribution, a pattern that we can well characterize. I think that this is what mathematics is all about, finding patterns in places where you might not expect it. And I hope that this sort of thing will infuse people to try to understand how ubiquitous mathematics really is in our everyday lives.
One of the world's first social scientists, Francis Galton, can arguably be considered the father of modern statistics. Through his groundbreaking work studying heredity, how characteristics are passed from parents to their offspring, he developed many of the concepts still used today in statistical analysis, such as standard deviation, correlation, and percentiles. Perhaps Galton's biggest contribution to statistics is the concept of regression to the mean, but it's a phenomenon that still causes confusion even today.
He started looking at how height is passed on as one of the characteristics within families, and he noticed that the tall parents didn't necessarily produce equally tall or taller offspring.
The children of those very tall parents, they tend to have heights which are closer to the mean height of the population. And interestingly, if you have very tall children, it will tend to be the case that their parents actually have heights which are closer to the mean of the population, which is a sort of counterintuitive phenomenon.
And that really puzzled him, so he looked at what is the principle there.
What's actually happening here, and what Galton discovered, is regression to the mean.
This tends to occur whenever we have a process which is either partly or wholly determined by randomness. Quantities like heights, which are partly deterministic but partly random, we get this phenomenon of regression to the mean. Maybe the height of the parent has some influence, but maybe nutrition, which is more of a random factor, has some influence. It might be that a very tall parent has just had good nutrition in that generation, but that their child won't necessarily have the same nutrition, and that might tend to pull them back towards the mean of this population.
Although Galton discovered regression to the mean through his work on heredity, it actually has nothing to do with genetics.
Regression to the mean is purely a statistical phenomenon. It's not due to any genetic process. It's just the fact that there's randomness in how tall you end up being that tends to mean that the children of very tall people will end up being slightly shorter than them, slightly closer to the mean. But it's a purely statistical process. It's nothing in our genetics which said that tall parents will have slightly shorter children.
And you can understand why by looking at the Galton board. The normal curve is essentially an indicator of the likelihood of certain outcomes for particular types of event.
When you have extreme cases of something happening, the likelihood of that same thing becoming more extreme next time is actually very small. The more likely outcome is going to be closer to the mean, which is described by the normal distribution. So if you look at how those ball bearings fall, if one falls in the extreme position, it's very unlikely that the next one will come there. All of the other space will come before that.
What you might do is to take the 10% of the beads which ended up furthest to the right and run them down the Galton board again. And what you would see is that actually these beads would be distributed evenly on either side of the mean, either side of the middle of the Galton board. And that is effectively demonstrating this idea of regression to the mean. Just because the beads were far to the right in one run of the Galton board, because it's a completely random process, there's no reason why they should be far to the right on the second run. In fact, they will tend to be clustered around the middle.
This may seem obvious, but you would be amazed at how often this phenomenon is overlooked when studying data, even today. Analysts have to be meticulous to avoid being tripped up by the effect and jumping to false conclusions. The difficulty is being able to determine whether changes in data have a direct cause or are simply the result of random statistical fluctuations.
Regression to the mean can be seen all over the place. You can see it in test results, for example. So you might get some students that are good and by luck on one test end up getting an extremely good mark. And you might have other students who are not so good and again by bad luck, for example, they get a very poor test result. So you might look at how should you treat these two different cohorts of students. Presumably you should praise the ones that have done well and you should maybe punish the ones that have done badly. But you might find on the second test that the luck for those students is reversed. So the good students may still be good, but they might not get the good luck, so they might go back towards the mean. Similarly, the bad students who got the bad luck in the first test might get slightly better luck and they might do better, which is a classic example of regression towards the mean. The problem is that then the teacher concludes, well, I praised these students who've now gone backwards, the good students, and I punished the students who did badly and they've done better, so maybe I should just punish all my students in future and hopefully they'll do better. But of course, that's just a fallacy. It's something which would happen anyway because of this phenomenon of regression to the mean.
Although there will be regression of results back towards the average, there might still also be a causal relationship between the teacher's actions and the student's scores. The key is determining whether it was significant enough to outweigh that inherent statistical regression. And one of the best ways to do that is for a study to include what's called a control group.
To take a cohort of students who haven't been punished or praised and seeing how well they perform would clearly highlight the issue of regression to the mean in these students.
The lack of such measures can totally invalidate the results of a study, and if it weren't for Sir Francis Galton and his Galton board, we might never have known why. The Galton board provided Galton with key insights into the distribution of human characteristics during his studies on heredity. It also played a pivotal role in his development of statistical theory, concepts that remain fundamental today. The distribution forms as beads navigate their way through a forest of pegs, arranged so that each time a bead hits a peg, it's randomly deflected to the left or the right with equal likelihood. This means there are many different possible paths a bead can take before it exits the pattern and comes to rest in one of the bins below. If you have a look at the middle of the pattern, you'll see there are lots of different pathways that take the beads to the middle bins. The further out you go, the fewer pathways there are.
There's so many combinations. So when you've got 12 rows of pegs, to get to the middle two bins, there's actually 462 different paths you can take to get through there compared to the single path you can take to get to the extreme outside bins.
But there's more to these numbers than that. There's a pattern here, and it's one of the most famous in all of mathematics, Pascal's triangle. A number pattern steeped in history, the triangle has been studied for millennia.
So we start from 1, and basically you will go on both sides of the triangle with a succession of 1s, but in the middle you will have values which are the sum of the two previous values above, and so on. So you quickly see how the pattern develops
And it's the exact same pattern of numbers that we get when counting the pathways a bead can take as it descends the Galton board. And that's because the bead's journey is a binomial process, and the numbers in Pascal's triangle correspond to the coefficients of a binomial expansion.
The binomial distribution itself comes from doing a series of what are called Bernoulli Trials. So these are effectively just flips of a coin, heads or tails, yes or no, 0 or 1. Combine a number of these individual Bernoulli Trials and you end up getting this binomial distribution. This distribution has a really nice link to what's called a binomial expansion. So if you take the expression x plus y to the power of n, where n is just some integer, some whole number, then you can expand that out. It's just multiplying x plus y by itself n different times. So you can write that out and you can get expressions like x to the n, x to the n minus 1 times y, x to the n minus 2 times y squared, and so on, all the way down to the other end where you have y to the n. Now each one of these terms will have a number in front of it, a coefficient, which tells you how many times that quantity, say x to the n or x to the n minus 1 times y, appears when you do this expansion. And those coefficients are exactly these binomial coefficients. The bi in binomial refers to the fact that we have these two quantities, x and y, that we're doing an expansion of.
The coefficients aren't just theoretical though, they have a practical use as well.
Binomial coefficients are typically used to find the number of different ways of choosing a certain number of objects from a larger group of objects. This is the mathematics of combinatorics. So for example, if I've got 4 people and I want to make a team of 2 people, I might want to know how many different ways there are of choosing 2 people out of this group of 4. And the binomial coefficient will tell me that there are actually 6 ways of doing this. And these binomial coefficients can be simply read off from the relevant row of Pascal's triangle. So if I'm looking at 4 people, then I look at the 4th row. I look at the second element that isn't a 1, so this is the first element, this is the second element, the 6, and the 6 tells me that there are 6 ways of choosing 2 people from a larger group of 4.
These combinatorics are very useful indeed when dealing with probabilities.
For example, if I'm thinking about flipping a coin, say 11 times, I want to know what's the probability that I get 2 heads. So I have to think of all the different sequences of flips of coins, head on the first flip or tail on the first flip, head on the second flip, tail on the second flip, so on. And I need to think of all the different ways that I can get 2 heads in those positions. So I need to know the number of ways of choosing 2 items from 11 items, and that's exactly this binomial coefficient, which I can read off directly from Pascal's triangle. It turns out there are 55 different ways that you can pick the positions of these 2 heads out of these 11 flips of the coin. If I then divide that by the total number of possible mutations, then I can calculate the probability of 2 heads in this flips of 11 coins being roughly 3%.
But how do we know the total number of permutations? Well, the triangle has the answer to that as well.
This is Pascal's triangle constructed of 12 different rows, so this would be row 0 up here, all the way down to 11. The total number of different possibilities of flips of the coin will be given by adding the numbers on the nth row. If I'm flipping a coin 3 times, how many different possible ways are there of doing that? Well, there's 1 plus 3 plus 3 plus 1 gives you a total of 8. Looking at the second row, then that's how many different combinations I can have of flipping 2 coins. 1 plus 2 plus 1 gives me 4. Flipping a coin once, then there are only 2 possible outcomes. I can have head or tail. As I go down, I can start to see a pattern emerging. These are all the powers of 2. Flipping the coin 4 times, if I add these numbers up, I find that there are 16 different ways of doing that. That's 2 to the 4, then 2 to the 5, 32, 64 ways, 128, 256, 512, 1024, and then by the time we're flipping the coin 11 times, there are actually 2048 different permutations of heads and tails that can come up.
And this is precisely what's happening in our Galton board with its 12 rows of pegs.
It's completely analogous to flipping the coins heads or tails. In the same way, we can look at the Galton board and try to ask, well, what's the probability that each bead will end up in a particular bin? If I have 11 rows, well, each time a bead hits this peg, it's the same as asking, do I flip a head or do I flip a tail? It's a binary choice. In effect, the total number of paths through the Galton board is 2 to the 11, which is 2048. So I have to just take the number of paths that I can use to get to that particular bin and divide by the total number of possible paths. So, for example, if I'm thinking of one of the middle two bins, then I say there are 462 different paths to get to that column, and I divide it by the total number of paths to snake its way through the Galton board, which is 2048, and I divide 462 by 2048 to find the probability that an individual ball will land in a given bin. Roughly a quarter of the time, and if I add both of those middle bins together, then it's roughly half the time I'd expect to find a bead in one of these middle two bins. There are mathematical formula for these binomial coefficients, but if you have Pascal's triangle, then you can work them all out for yourself. It's a really nice system which you can just put on top of the Galton board, and you can see exactly how many beads you would expect to make their way through to each one of these bins. And as we've already seen, it ends up looking like this beautiful normal distribution.
In a sense then, the Galton board can be viewed as a dynamic version of Pascal's triangle. The number pattern emerging out of the various interweaving paths the beads take on their journey. Truly math in motion. If you would like your own Galton board for use in your school, museum, office or even at home, then go to galtonboard.com.